Right. So, we will continue our discussion of this Hertz dipole. The only sort of thing to remember about this Hertz dipole was that it was a very, very small current element, and because it was very small, we can assume current is approximately constant. Right? So, what are the steps that we did? Given the current, we could calculate the A vector using this relation over here, convolution of a known current with Green's function. I got A, from A I got H, and H I calculated a little bit cleverly, making use of both Cartesian and polar coordinates, right. When you are seeing something like r cross z, so I have mixed up these coordinate systems and I have got a very nice expression over here. And we notice that far away the fields go as 1 by r. Okay. And then we said that the electric field is simple to obtain once I get the magnetic field just by taking the curl. Right. So, if I now go to take the curl of this expression, you can sort of see what coordinate system will I use? Spherical, right, because it has r, theta, phi, everything is there inside it. So, spherical is the best thing. Do you think it will be a very beautiful expression? Right, it is going to have everything in it, right. So, I am not going to write down that curl operator and derive it, but this is the whole expression over here. So, this is the magnetic field which we already saw, the first expression. And the second is obtained is sort of when I take the curl of this, I get two components. So, there is a, this was in the phi hat direction, then I have a theta hat and a r hat. Okay. So, just to remind you, this is my r hat direction, right, which way is, this is my theta and this is my phi. So, theta hat is pointing downwards over here and phi hat is which way? Into the board, right. So, this is my phi hat. That is what this coordinate system looks like. R hat dot z hat was written, sorry, cross, r hat cross z hat was written as sin theta phi hat minus, right. The direction between the, I mean the, perpendicular direction is phi and the angle between them is theta. So, sin theta, right. The unit vector, so mod r mod z is 1, fine. So, this is the expression you get. You notice that the expression for the electric field is fairly sort of scary looking, but this is the exact expression. Okay. There are apart from the fact that the length of the dipole is small, there is no other approximation in it. Right? So, looking at this, the first thing to do is let us take a simplified version of this. When we say that we are going to look at what are called far fields. Okay. In this problem, very naively I am going to say far field is when kr is much greater than 1. Okay. There are more refined definitions of this, we will come to them later. Under this approximation, what happens to the magnetic field? I have two terms, right, in this bracket. I will just keep the first term because kr is much greater than 1, right. So, in that case, the magnetic field magnitude becomes, I mean 4 pi is j k, right, e to the minus j k r by r sin theta phi hat. What happens to the electric field? From how many terms are there? 5 terms, right. So, I get to keep, I should keep the most leading term will be just one of them, which is the 1 term, right. So, this will become I delta z by 4 pi j omega mu e to the minus j k r pi r sin theta hat. Okay. So, that is why we say that in the far field, the fields are going 1 by r, right, in amplitude at least, as a function of r it is going as 1 by r. Okay. So, we have already made one comment about how this is different from your Coulomb's law, right. Okay. Anything else that you can notice from here? there is a lot of interesting physics happening over here. So, what is it saying? When I go stand far away from the source, what do the fields look like? So, which way will the pointing vector be? So, pointing vector S is defined as half of E cross H star, H conjugate, okay, in phasor. So, which way is my pointing vector? R cap, right. So, my pointing vector is along r hat and my electric field is along theta hat, my magnetic field is along phi hat. What kind of a configuration is this? What does it remind you of? It reminds you of TEM. Yeah, it is a transverse electromagnetic wave, because the electric field and magnetic field are perpendicular to each other and they are perpendicular to the direction of power transfer. Isn't that also the case in a plane wave? Yes, right. So, this is your TEM wave. No component of electric or magnetic field in the direction of propagation. So, this is the simplest kind of wave that we have studied, right. In fact, it looks identical to the 1D plane waves we have studied. Only difference is that there is a 1 by r in the denominator, and so we call this a 3D plane wave. Right. So, what do you expect will happen to this pointing vector? We already noted that it is going to be in a direction in the r hat direction, in the r hat direction. What will be the magnitude? So, there is going to be a half, this whole thing is going to be there, I delta z by 4 pi, okay. J into minus j is going to give me plus 1, right. So, I am going to have a k omega mu, right. So, k omega mu, what else? Pardon me? H conjugate, that is why j becomes a minus j, whole squared, correct. And sine squared theta divided by r square in what direction? R hat direction, right. I think I have got all these terms. Right. Now, so I have got a power that is going as 1 by r squared, okay. So, you should keep this in mind. This I have derived for a Hertz dipole, but this is true for any antenna structure in general. Far away from the antenna, even if you take the base station, the mobile base station, and you go far away from it, you will find the fields coming from it are of this form, okay. So, if I integrate, if I want to find out how much is the total power leaving this, right. So, what would I do? I would integrate, supposing I wanted the total power, I would integrate this pointing vector over what? A sphere of radius some r, right. So, if I did, for example, ds over here, so you can do this calculation, right. This is not a very difficult calculation. Find a surface element on a sphere and integrate. This is going to be a what is your ds over here? Okay, little bit more generally, r dr r sin theta d theta d phi, right. So, when you integrate this for constant, over, you will get 4 pi r square, which is the surface area, right. Sorry, there is no dr. So, it is going to be r squared sin theta d theta d phi. Right. So, when I integrate this over the surface, what will happen to the r square term? Cancels off. So, the answer, we can do this integration, but it is not very interesting, right. The answer is independent of r. So, what does that tell you? No matter where, this is also makes physical sense. No matter where I integrate from, the power leaving the sphere should not change, right. So, that is what I get. This is just confirming our intuition, because a sphere encompasses the entire 4 pi steradian. So, the power, if I calculate, because it encloses the dipole, whether I integrate here or here, the power that is leaving the surface is going to be the same. Power density on the sphere will be different. That is captured by S, and you can see as you get closer at smaller r, power density increases because it's 1 by r square, right. The other thing to note over here is this S expression over here, it is purely real. Even though there was a good chance that something could have become imaginary over here, because there are all these j's and so on in the field expression. This is purely real, right. So, this is it's what circuit element has purely real power dissipated in it? Resistor, right. So, this is like the if you wanted to make a circuit equivalent of it, it's like power that is going in through a resistor. It's once it goes, there is no way to recover it, okay. So, this is also called, so these are called radiation fields, and this is called radiated power. Okay, no, I think there is a very simple sort of confusion over here. This is the power pointing vector, this is the pointing, this is the density, right. So, this is total power, okay, I am calling it total power, power integrated over a sphere. If I go very, very far away, the power is still there, it is going as 1 by r square, right. Even if it becomes very, very small, I am also integrating over a very large area, if you want to think of it that way, right. So, it is going to be there. Pardon me? Yeah. Yeah. So, if this is my antenna over here, there is some power over here. If I go further over here, right. So, the power is this, I mean, let us say a pointing vector. The pointing vector is going as 1 by r square, right. So, it is going to drop. So, it's low over here, it is even low over here. Power is dropping, that is okay. But now, if I integrate over this whole thing over here, I get the same number. That is what you expect, right. You go far away from the source, the field intensity drops. So, this is your near field consideration. Now, not surprisingly, the other thing that we should look at is, so this is far field, the other thing we should look at is what happens in the near field, right. So, in the near field, what we can say is that Kr is much less than 1. So, I am looking at regions very close to the antenna, right. So, what happens to these expressions? So, H for example, which term will I keep? The second term, right. So, 1 by Kr now is much larger than 1, right. So, I will get I delta Z by 4 pi, the J and the J cancels off. So, I get a K by R, sorry there is no K, it will just become the J and the K cancels off. So, I get a e to the minus j k r by r square sin theta phi hat. So, magnetic field anyway is in the same direction. Electric field, let us see what happens. Electric field, which term should I keep? Only the 1 by j k r square term, right. So, I am going to get I delta Z by 4 pi, okay, j omega mu, then I have 1 by j k r squared sin theta hat, okay, sin theta hat, and then I have a e to the minus j k r by r theta, okay. And one more term is there, this is new. So, I have a j omega mu, then I have a 1 by j k r whole squared, I have a cos theta along r hat direction and e to the minus j k r by r, okay. So, in contrast to the far field case, the magnetic fields are going as 1 by r squared, the electric fields are going as 1 by r cube, right. 1 by r cube reminds us of what from electrostatics? The electric field due to a dipole, right. So, this is acting like, it seems like a dipole, right. So, now if I calculate the pointing vector in the near field, okay, same thing I will do half of E cross H conjugate, okay. What do you expect? A lot of terms, right, yeah, but I mean what are the essential features over here? I should get a 1 by r to the 5, 1 by r 5. What directions will I expect? So, there is a theta cross phi. Theta cross phi is going to give me a r cap, right. So, I am going to have sine squared theta r hat, and then I have r cross phi, which is going to give me something along theta, sine 2 theta, because cos theta into sine theta along theta hat, and a bunch of constants. Okay. Which are not so important. Well, what is important about these constants, let me just write it over here, is that this has a j into something. Okay. You can see that because E cross H conjugate, E, both the terms of E, they have a j, H has no j, right. So, one j term is going to remain over there, right. So, what are the key features is 1 by r 5, then it is purely imaginary, right. So, this is different from your previous case. So, these are called your reactive fields. Okay. Now, if I ask you, if I integrate over some sphere over here, what should you get? Will it be r dependent or not? So, it should be 0. Why should it be 0? No, it won't be 0. So, one answer is that it will be that the integral will be r dependent. It should not be r dependent. What is the catch? No, I am not integrating over the source. The source is there and some small distance away from it I am integrating. No, so actually the thing is that when we wrote down these electric and magnetic fields, we made the approximation kr much less than 1. Now, if I want to find out the total power leaving the sphere, I should include all the terms, right. If I do that, I will find out that the power is independent of r, and that makes physical sense. The amount of power leaving it, right, will not change. But here I am taking only out of these 5 terms, I am only keeping 2 terms. So, there will be some sort of mismatch over here, that is okay, but we are not, I mean the main point is we are not going to integrate this term over the whole sphere. Okay, this is just telling us what is the dominant part of the Poynting vector, what is the main contribution to Poynting vector in the near field. So, this fact that it is purely imaginary and reactive reminds us of which circuit element? Inductor or capacitor, right. So, what happens in the near field of any antenna is that the energy keeps shuffling between the electric field to magnetic field. Like in a LC circuit, energy goes from an inductor to a capacitor and back and forth. Same thing happens over here. Okay. So, this, I mean back and forth keeps happening, and there are you have heard of these wireless power transfer applications, right. Those work best when you do it in the near field, because you are able to access this energy. By the time you come to the far field, it has become purely real. So, it is only a resistive drop. But here this energy can be exploited. So, for example, these toothbrush chargers and all, you dock it over there. So, stuff is happening in the near field. You are able to transfer more power. There is one more. Negative signs may be there. I mean, this is bunch of constants over here. Theta cap. It is r cross phi, right. So, r cross, that is minus theta, right. So, there is a minus theta. Where do you see a j square? There is no j square. Oh. Yeah, well, the expression is correct, because in the other case, what term do you get? You have a phi cross. No, again theta cross phi. What is theta cross phi? Positive r, but there is also a minus term there, no? Yeah, there is a full. So, all of those constants are inside this bracket. We do not care about it. Relative to these two, there is a minus sign. Okay, so reactive fields and energy is transferred between the E and H fields. Yeah. The total power is going to be conserved. Yeah, the actual pointing vector will be conserved regardless of what R you choose to integrate. Okay. So, in a course on antenna theory, we would spend a lot more time deriving this and understanding all the features. We want to sort of get to the CEM, computational electromagnetics part of it. So, this is just by means of giving you some introduction to it.